Welcome back then. Happy Wednesday. Did you have a happy Halloween? They're like, yeah, whatever. We handed out candy. As I had anticipated, Huey insisted that we needed to hand out more candy at 6:30 this morning when he got up. I'm like, no, dude, that only happens once a year. But I think we're going to have the same conversation repeatedly because it was so exciting that all the kids came to the door. Yes, indeed. Why is this blinking red and green at me? This must be something about my internet connection. I don't know. We'll figure it out. So, we're talking about piecewise models. Remember that stuff? Should we do a little bit of reviewage? Not to be confused with sewage? Yes. So I may have mentioned this before, but this semester I am also getting to be in your shoes for a change because I'm taking piano lessons. So I have a renewed appreciation for the value of a good review. Because just because I said it once doesn't mean it's still there the next time you come back, right? So yes, I've also have a new appreciation for not calling things simple. That's like, this is simple to you, but it's not simple to me. So yes, big picture. What have we been talking about lately? So this whole thing with the audience participation, I know some of you are never going to say anything, even if like I had a gun to your head, like you're that afraid of looking silly in front of your classmates. So how about we revise? How about I ask a question, I pause long enough for you to come up with an answer inside your head, and then I tell you what I think the answer is, and you can compare it against your own version. Do you think that would work better? Because some of you don't want to talk, right? Or you can even type it. Right? If that way you have like a record of your thoughts. You can like journal during a stats class. How cool would that be? Write a reflection piece about how this makes you feel. So yes, what have we been talking about? No, I want you to answer inside your own head or write it down. I'm going to pause long enough for everyone to come up with an answer. I think we've been talking about modeling change over time. That's what I think on a broad picture. And I think we've been talking about ways to address nonlinear change over time. Such as, what are the family of models called where you take time and square it and cube it and fourth it and stuff like that? Starts with a P. Polynomials, yeah. Yes. So good things about polynomials as an approximation, they're straightforward to implement, meaning that you can use existing software. All you have to do is square your variable or cube it and put it in. They are relatively straightforward to interpret, right? The linear, if you have a linear trend, that's constant change over time. A quadratic trend implies a change in the rate of change. Give me other synonyms that go with quadratic. One starts with an A and one starts with a D. Acceleration, or its opposite, deceleration, yes. And what's the tricky part about interpreting what a quadratic trend does? There's a constant you have to throw in front of it, right? It's either going to be 2 or 1/2, depending on the way you say it. So I'll give you a sentence. Blank, the quadratic, is how the linear rate of change changes per unit time. And the correct answer is either 2 or 1/2. It's twice, yeah, twice the quadratic is how the linear rate of change changes per unit time. Because the quadratic is half the rate of acceleration or deceleration. So what might be bad about that as an option? Let me pull up a picture, jog your memory here. Here is a picture, for instance, of the example data we're looking at, where I have 6 means over time with the solid black line. I have the fit of a linear model here, and then I have the fit of a quadratic model. Exactly. It comes back. What goes up must come down, and what goes down must come up. And that doesn't often happen. Certain types of phenomenon might follow that type of U-shaped trajectory, but it's pretty rare. So from a theoretical perspective, it's a little bit impoverished, but it does a good job of matching nonlinearity when you have relatively few occasions. The key thing about these models, polynomial models, is that they track continuous trajectories. So even if you have a lot of occasions, they're working together to build a overall trajectory. An alternative way of approximating nonlinear change we started with at the end of last time, these piecewise slopes models. Hopefully by the end of today we'll start looking at exponential models as well as another type of change. So each of these types of models has 2 kinds of effects related to time, right? One starts with an F and one starts with an R. Fixed and random, yes. See, this is working great. What do fixed effects do? What's their job? Everyone gets the same. Yes, that's keep talking, keep thinking. What is their role? Average, yes. They describe the average trajectory. So that means they're on the model for the mean side or the model for the variance side? Means, yeah. They are predicting the means over time. That's what fixed effects of time do. And since they're fixed effects, do they explain variance or make a new pile? Fixed effects, explain variance or make a new pile? Explain, yes. So this is where staring at equations sometimes can be helpful. Let me pull up the equation for the random quadratic model, for instance. The fixed effects of time and time squared are in the level 1 model because they are time variables, not person variables. And that means those fixed effects explain what kind of variance? Level 1 or level 2? We got answers for both. So let's reason our way through this. First off, which letter is level 1 versus level 2? Level 1's this one, right? Level 2 are the U's. In general, what's the rule here? Fixed effects explain the variance that it's in its line. So time and time squared reduce this E variance, which is level 1. Right now, nothing in the model is going to explain level 2 variance because only person predictors can do that. U variance is person variance. It's differences across people in intercept, linear slope, and quadratic slope in this model. So we need person predictors to explain that. That's coming up after Thanksgiving. So if fixed effects explain variance, that must mean that random effects make new piles, right? So in this model that you have up here, how many different random effects are included? Three. 3 U's. U0, U1, U2. What U0, what U1, and what U2 mean is entirely specific to what these betas mean. In this model, beta 0 is the intercept, therefore U0 is a random intercept. Beta 1 happens to be the linear time slope in this model, therefore U1 is individual differences in the linear time slope. U2, because it's referring to beta 2 here, is individual differences in the quadratic. So these are each phrased as this person's deviation and intercept, slope, and quadratic slope. What the model actually estimates, though, for that is the variance across the intercepts and the slopes. If I were to ask a homework question, for example, hypothetically, as to where you might find the variance in the linear time slopes, where do you look? Give you multiple choice here. You can look in the R matrix, you can look in the G matrix, or you can look in the V matrix. What do you think? And the code actually gives you a hint, by the way. Because you see the word random here? And you're listing the random effects. And after the slash, these are options for what SAS is going to print. By the way, if you don't enjoy scrolling through a mountain of output, take these things off. You don't have to have them. But we've got G and G core and V core, which means it has to be one of those two, because those are the ones that get printed with the random line. G. Yes, V is what you get when you put G and R back together again to get the full data matrix. Yep. What's the difference between the G and G core, or the V and V core, or the R and the R core? I don't have that one in here, but I could. What do each type of matrix tell you? What does core stand for? Correlation. That means the non-core kind has to be what kind? Variance and covariance, yes. So these are optional pieces of output that help you decipher what the model output is, what it's predicting. I sent out an email yesterday after getting like my 4th question on the same topic. These 2 letters right here, IC. If you want to use my macro to do fit tests, you need that option. That stands for information criteria, and it generates the output that you're saving here. So you need both of those things for it to work. Okay. What else? What am I forgetting? Think we covered the big stuff? You want to talk about pieces? Reese's or otherwise? Sorry, we gave out all the candy, so I couldn't bring any in. It was very sad when we finally had to shut the lights off. Let's talk about pieces. And we'll review absolute fit again, because we're going to do it again too, so we'll do that again on this context. Here we go, pieces. Piecewise slopes models. So these are have to know change occurred. The change in procedure occurred, for instance. So if you wanted to look at, say, a progression of a disease, you could have a pre-diagnosis period and a post-diagnosis period, but you have to have a date for diagnosis to make that work. Otherwise, there's no way to differentiate the two. Also, you'd have to know at what point someone started treatment, for instance. So as long as you have a date that you can designate as the shift in phase, these models will work for you. If you don't, then that's a different kind of model called a latent change point model where you're trying to look for where the breakpoint should be instead, and it takes a lot more data to do that. I am using these models on our current data in an atheoretical fashion because it happens to fit somewhat well. But the equation for a two-piece model looks remarkably similar to the equation for the random quadratic model. Each component of the trajectory, intercept, first slope, second slope, has the potential for a fixed effect and a random effect. Fixed being the common part, random being the deviation from the common part for which you estimate a variance. So in the present example, I started with just fixed slopes, and we got to the point where we're going to add random ones. So I'm fitting a two-slope model that's going to look like this to the current data as a way of approximating the nonlinear trajectory. And I'm calling this my early practice effect and my later practice effect. To set up the codes, we did talk about this. Pick this up on slide 30. We're creating brand new variables to represent the type of change question in the back. Sir. It's possible to do this because I have extra room in the back to wiggle with. In general, the same rules about the reliability of change would apply. This first slope is not going to be measured well because I only have 2 points. If this were something where I was going to deliberately design my study to sample an early practice effect and a later practice effect, then I might try to have more occasions. But in this case, the occasions are actually equally spaced because all I'm keeping track of is how many times you've practiced it, as opposed to like whether you've practiced once a day or twice a day or 3 times a day or something. So yes, it is potentially a concern, but not one that I can do anything about after the fact. Yes. Okay. So I'm building my time slopes here to represent change during each phase. And in this way of coding, what I'm going to get out of the model is the rate of change during each phase specifically. So the orange here describes the rate of change between session 1 and 2, and it shuts off after that, as indicated by the last value being held across the rest of the occasions. Analogously, my purple slope turns on at time 2 to capture the change from time 2 to 6. It is inactive, it is shut off at the 0 value here beforehand. So the two of them work together to describe each part of the trajectory separately with a linear slope in each case. Now riddle me this. Could I conceivably have a quadratic slope 2, 6 in my model as well? I know it doesn't look like I need one per se, but could I do it? Let me put this picture back up again. Hang on, let me find it. That. Could I have a quadratic purple slope? Yeah, how many occasions is my purple line fitting? How many dots? 5, right? So could I have a quadratic slope through 5 occasions? Sure. Could it be fixed and random both if I wanted to? I could actually in this case. It's n-2 for the number of random slopes related to time. So having 5 dime points over here to work with, in theory, I could have a quadratic slope that's fixed, meaning the average line gets bendy, and we could have individual differences in bendy. How about my orange line? Would it make any sense whatsoever to have a quadratic orange slope? No. 2 points make a line. You're done. That's like having a quadratic effective group when you have only 2 groups or something. It doesn't make any sense. There's only one difference that you can model. So with respect to orange, One fixed slope and one random slope for that is all I can do. Purple, I could have something that's linear or nonlinear as I see fit. So even though these are often described as piecewise linear models, they don't have to be. That's my point. Okay, so let's look at the example for that. We did this before. Setting up the coding. This is what it would look like if you had balanced data. You're only able to assign integer values if everybody has the same possible values. Otherwise, if when session 2 happened is different across people and when session 3 happened is different, you have to save that information as a variable and use it to create the slopes. So that would look something like that. Let's see. Nope. Let me find it. This one. This is an example of what it would look like in SAS to create a piecewise slope model with unbalanced time, where what time it is at each of the sessions is saved as a variable, and I find the phases as the difference between those variables rather than just putting in integer values. I'd be happy to help set that up if anyone wants has a design in which they're thinking of doing that. It can get a little tricky. So I've created my slope variables here to reflect early and late change. I have my fixed slope 1, 2, fixed slope 2, 6, comma, random intercept model. I'm trying to be as clear as possible in both my words and my equations to designate how many random effects are in this model right now. How many level 2 random effects do I have? In other words, how many U's do you see up there in that equation? Just one. Random intercept means parallel change, right? So at this point, everybody changes the same. They just get to have a different starting point. Let me keep this equation up here. I've just introduced 2 fixed effects for these slopes. Fixed effects explain variance or make a new pile? Explain, yes. We did this one like 5 minutes ago, so I know you remember it, right? And which one do they explain? E that's in its line or U0 that's not in its line? E, yeah. Slopes for time are time things. They explain time variance, which is E. Slopes for time are not people things. U variance is people things. All right, so here's my slopes. So fixed intercept 1961. That is expected response time when, answer to yourself, time equals 0 is the definition of the intercept. So time is 0 when both slope 1, 2 and slope 2, 6 are coded 0, which occurs at which session? Session 1. Here we go. From there, response time declines. People get faster as they get more practice. Between session 1 and session 2, on average, people decline by 163 milliseconds. That is significant because I can stare at this p-value and it tells me so. After session 2, are people still declining? Yep, I can stare at this p-value and tell you that that's significantly negative. They're declining by 33 milliseconds a session on average. Do these two numbers right here tell me if they're declining less after session 2 than before? It kind of looks like it if I just eyeball them. How do I find that out? I got to ask for it, right? How do I ask SAS to do math for me? Estimate statements. Since those of you who are not native to SAS, let's see, state of people, sociology folks, right? Yes, Scott and Lucas, where are you? There you are. And Sarah, do you, yeah, she doesn't want to admit to being a sociology folks. She's like, I'm not raising my hand. Do you know what this is called in Stata, estimate statements?
I'll be honest, I use SPSS a lot. I get grief for it in the sociology report.
Okay, well, I'm going to improve your soc cred. They're called LINCOM, and also margins. Would you like to know what it's called in SPSS? No, she's like, no, I'm good. Well, I'll tell you, test. What's it called in M+? It's the new parameter within model constraint. And what's it called in R? It is a special package called GLM blah blah blah. You heard it here first. I can never remember what it's called. I just know that there is one. Point being, every software package in the history of man knows how to do math for you if you know how to ask it. Knowing how to ask it is the hard part. The reason that you were never taught this in SPSS, by the way, is that the test statement is not available within SPSS, GLM, regression, or ANOVA. It's only available within mixed. So there you go. That's why you weren't taught it in the first place. And if I ran the world, I would change that. But I don't run the world. Only for an hour and 15 minutes twice a week do I have a tiny corner of running the world. So yes, I am asking SAS to do the math for me to find the difference between the first slope of 163 and the second slope of 33. Whenever you invoke a negative number here, you're asking for subtraction. So the words slope 1, 2 refer to the fixed effect of slope 1, 2 as estimated by the program. The word slope 2, 6 refers to its fixed effect. So it does the math for you that you're requesting. And lo and behold, here's my 130. Now I will note that you don't need to ask SAS to do that math for you. Even in my head, I could do 163 minus 33, right? I got that one. But what can't I do in my head as quickly? If it's significant. Now yes, actually there is a formula, and I could teach it to you by which you could compute the standard error, and then you could go to your t distribution and look up your p-value. But we have lives to lead. So I don't want you to compute anything that you don't have to. SAS will do it faster and more accurately. So yes. Now, the fact that you can compute the right answer is a great way to check that your estimate statement is correct. Because you can do the math and be like, if I got this right, it should say 130, and then you can about that. So in the book, I added a quadratic slope 2, 6 just to see if this needed to be a little bendy, and it didn't. It wasn't significant. So I said, okay, that looks like it's good enough. After we get done with the random effects, we'll check to make sure that it really is good enough, meaning that it actually does fit these 6 means. But for now, we'll do the random side. So I have explained 24% of the residual variance with these 2 fixed effects of time. I'm now one at a time going to add random slopes. When we did this for polynomials, we added linear first, then quadratic, because those terms are hierarchical relative to each other. The same is not true for the pieces. You don't have to add the linear slopes for these pieces in any particular order. I started with the first one because it was first. I didn't have any better reason than that. Based on just staring at the spaghetti plot for these data, which is right here, it kind of looks like there might be more variation to begin with than towards the end, but that's admittedly just a judgment call. So I'm adding slope 1, 2 to my random line. It shows up then here in my G matrix. So 1, 1, that's my intercept variance is labeled here. 2, 2 in the G matrix is my slope 1, 2 variance. And that same number, 59,941, is on my list of estimated terms here in the model for the variance. 60,000, that looks like a lot. Doesn't it look like a lot to you guys? Does it look like 0 or maybe bigger than 0? I don't know, 60,000 seems like a lot to me. And if I compare that to my walled test here, it says it's different than 0. Am I allowed to look at that? No, that variance is on the wall. No walled test for things on the wall. What do I do instead? Mild comparison, yep. And I have it, let me open up. So this is the spreadsheet that goes with this Chapter 6 example. I just put up a new version of the zip folder today. I'll get to that, why that is in just a second. But if you don't want to use my macros, or you don't, or they won't work for you, you can always type it in yourself. So here are the log likelihood tests for this example. Here's the first one. So we have a difference of 63 on 2 degrees. And why is it 2? Because I only added one more u into my model right here. Yeah, what's the other thing? Remember? Yeah, this, right? Yes, I will accept this as an answer. Thank you. Gestures are allowed. I'm going to go ahead and assume that by this you mean this whole line, right? Yes. So we added the covariance with the intercept. That's why it's 2. Because how you start and how you change gets to be related, because they both came from you. So yes, we keep that random slope. I do want to point out what this model says, though. If you're in a situation in which you don't have random slopes for all of your pieces, it's important to keep this in mind. Here's my V matrix. V matrix, again, is the prediction from putting level 1 back together again. So on the diagonal are the predicted variances at each occasion. On the off diagonal are the predicted covariances across occasions. Now, do you see a pattern here? It's kind of a funky pattern. You make it bigger so I can go over and stare at it. So I have a different variance at time 1 than I have at all the other times. Likewise, I have the same covariance from 2 to 6, but a different covariance from 1 with all of the other ones and 1 with 2. So this is a half compound symmetry matrix, right? Basically what we're saying is that the variance between time 1 and time 2, it gets to change because there's a random slope on that part of the trajectory. So the variance and covariance gets to change over time between 1 and 2, but from 2 on, there is no random slope. From 2 on, there's just the random intercept. So that's predicting a compound symmetry model. The reason I point this out is for situations in which you only have 3 occasions and you want to have some kind of piecewise model. Here, I'm going to break out paint because I haven't done that this year. Here's my graph, right? Let's say, for instance, you have the make babies mad and watch their cortisol response study, right? So here's baseline, here's mad baby, and here's okay baby, right? And you're interested in the slopes for each of these 2 pieces. How many random slopes can I have if I only have 3 occasions? I can have a random intercept, and I can have 1 random slope, but can I have both be random? I can't, not and still have a residual. I'd have to shut off the residual variance and say that the random slopes explain all of the variability and that there's no variability left. So that's not likely to be the case, and I wouldn't recommend it. But if you were to decide to have only one random slope, for instance, let's say that you pick that one, then you're saying that the variance at baby freakout gets to differ from the variance at baby happy again, but that baby freakout and baby at the beginning are the same. So it's like a weird, half the data have the same variance and covariance, but the other half don't, when you have only one random piece in a two-piece model like this. So in that case, I wouldn't do random slopes. I'd go back to unstructured, because unstructured allows the variances and covariances to be whatever they want. You don't have to worry about falsely assuming variance and covariance is the same for any part of the trajectory. And since there's only 3 occasions, odds are good you can pull it off. So that's what I would do in that case. So we do have one significant random slope. We can do the same thing to test the random slope on the other part. Add U2, pick up slope 2,6 on the line. How many words are highlighted right now? 3, yes, so these are the trick ones, right? That means I have just added how many parameters? 3. Yes, this is the shortcut you can use. Because whenever I've added my third thing here, I have added the slope 2,6 variance and its covariance with the things already on the line. So that is 3 new parameters in my model. U2 is right here. Covariances don't show up in the equation because they don't contribute to predicted values. If I were to write out the matrices, then you would see them in there. But I don't need to write out the matrices because SAS will do it for me. So here's my new slope 2,6 variance, 2,617. That looks pretty big. Now I have a V matrix in which the variances get to differ over time and the covariances get to differ over time in a particular pattern. That's implied by my 2 random slopes. I can do a likelihood ratio test to see if it's significant, and lo and behold, it is 44 difference on 3 degrees of freedom. Should I do some sort of pseudo R-square to talk about variance explained by my random slopes? I didn't explain anything, I just moved it around. A random slope is a deviation from the fixed slope for currently unknown reasons. Each person needs their own slope, but we don't. So we haven't explained any variance, we have reallocated it to a new level 2 pile. What you can do to try and convey some kind of effect size is what I have up here, random effects confidence intervals. These describe the ranges under which 95% of your sample is predicted to fall in each effect that's random. So I have a random intercept that represents response time at the beginning. That's predicted to go anywhere from 900 milliseconds up to about 3 seconds. So there's a lot of variability in the intercept. The initial slopes are predicted to range anywhere from 650 to 322, but note the change in sign, right? This confidence interval overlaps 0, and so does this one. I'm going to be reviewer 3. Your confidence intervals overlap 0, so that means they're not significant, but then you said they were. So I'm confused. Your reviewer 3 is always indignant. How do you attend to reviewer 3's complaint? Dear reviewer 3, step 1, apology. No, I'm not kidding. I'm serious. This is how my response letters work. When they don't get it, it is your fault. Even if you said it already, it is your fault. You apologize because you were not sufficiently clear. You appreciate their feedback. As now explained more clearly on page 26. What do I say? I go 2 standard errors on either side of that, that's my best guess for what the average slope is. These confidence intervals are about the random effects. They're about the range of the people, so it's a different thing. This confidence interval of minus 659 to 322 is not what we expect the average change to be, but what we expect the individual changes to be. And yes, on average, people go down. They get faster from time 1 to time 2, but that's not true of everyone. The amount of variability around that slope, as given by the random slope 1-2 term, implies that some people go up and some people go down. And the same is true here. On average, people are still improving at a rate of 33 milliseconds a session. Some people's rate of secondary improvement is all the way up to 133, and others are actually getting worse. So again, these are predictions. You can't talk about them as if this is an actual realization of a person, but based on the model predictions, this is how you would characterize the variability in your sample. Okay. Very good. With me. Feeling good? Any of that you want to hear again or ask questions about? Okay. I want to show you the exact same models a different way. The term is a mouthful, reparameterization. That means defining your parameters differently to give you something that is more convenient. So let me go back to Paint here and give you a sense of when this reparameterization that I'm going to show you could be useful. I need a new one. I don't need to save this beautiful drawing. So let's say you're an educator and you come up with a brand new way to make kids learn more. So here is the beginning of the school year, and here's the end of the school year. And if you did nothing, kids learn more already, because that's called school, right? That's the point. What you want to know is if they learn more than they would have already, right? What you want to know is, like, if you switch things up in January, and you have like a control group that didn't get anything new, you hope your treatment group takes off like this. So the question you're interested in here is not whether or not there's change in the second semester, but whether there is more change relative to something else. So this is the basis of what I call slope and deviation slope, because you can trick your model parameters into giving you that information as part of the model directly. If there is no differential change, that's characterized by this line right here, in which case there is no need for a piecewise model. It looks like, to the best of my paint drawing ability, this is a linear slope, whereas this group has a deviation in the slope and potentially in the intercept. So you can test the deviation aspect rather than just whether there's a slope at all. If that is what you want to know, is if people have changed differently than they would have otherwise, this is the way you set it up, as a deviation slope instead. So let me show you what that coding system looks like. This is on slide 31. So I'm going to flip back and forth so you can see the difference here. This is what we were doing before. This is what we're doing now. Before, now. Before, now. It's the orange part that's changing. Watch the orange numbers. Eat. Eat. Let's cut out purple for a minute here. Just stare at those orange numbers. Does that pattern look familiar to you? That's just time centered at 0, right? Like centered at session 1. Yeah, not a coincidence. Because that is what would happen if there was no differential change in the second period. The purple, even though it's coded exactly the same, has a different interpretation now. If you think about what the definition of a unique effect is in any kind of linear model, all the way back to regression, right? Unique effect is the effect of a predictor controlling for all other predictors in the model, right? So purple, because orange and purple now are tracking the same thing here, purple's job is to pick up the extra part that orange didn't. So it's the effect of what happens to the trajectory after time 2 that wasn't already happening. Likewise, orange is going to have to become orange after controlling for purple, and the only part that's unique to orange then is right here. So what's going to end up happening is that orange is still going to be the rate of change between session 1 and 2. Purple is going to become the difference in the rate of change after session 2. Not the rate of change, but the difference in the rate of change. So I'm going back to fixed slope models set up this way instead. Where I am now back to using time 1 instead of slope 1, 2, but the same slope 2, 6 that we had before. So there's 3 potential pieces of information that we might want to know. Is there a significant change from 1 to 2? Is there a significant change from 2 to 6? And is the rate of change from 2 to 6 different than it is from 1 to 2? Any one model can give us 2 of those 3 things, but not the third because it's redundant. It's a linear combination of the other 2. So the first version of this piecewise slopes gets you the significance of change within each epoch. The thing that I'm going to show you now gets you the difference in the rate of change between epochs. Here it is. I'm still going to ask for the missing piece of information just for completeness here. So here are my fixed effects. Rate of change from 1 to 2 is now carried by the time slope variable, minus 163. Slope 2, 6 picks up the difference in the rate of change after session 2. There's my 130. So if I take the rate of change as given by time 1, and I add to it the difference in the rate of change after time 2, I can get what the slope actually is from 2 to 6. If I add minus 163 and 130 together, I get my minus 33, and that's exactly what I've asked for right here. The third thing that's a linear combination of the other 2. And there it is. So I didn't put any of the variance components or the model fit information on here because this is literally the exact same model as the other version that had fixed direct slopes with just a random intercept. It's a rearrangement. I wanted to show you both versions because one may be more convenient based on what you're trying to study. We can add our random slopes to the model. So here's my random slope 1 for the effect of time. That's just like saying I have a random linear slope. So I put that here. So what I'm saying then is that people get their own rate of change, and that rate of change carries throughout the entire study. People may change differently after intervention, but the way that people change differently is the same. Let's say that again with my picture. This current model with only a random slope for the time part says that people get their own slopes, and that rate of change carries throughout the study. If there is this difference in slope here, everybody shares it. Everybody gets the same bump from being in my new fantastic intervention program. So we test our random slope the same as usual. Likelihood ratio test says yes, random time slope is significant. And then in the last step, we add the slope deviation as random. Here's my confidence intervals for that, and here's my significance test for that. And at that point, this truly is an identical model to the last one that we ended up with 2 random slopes. It's just a rearrangement of what the slopes mean. And here's my picture. So since they fit the same with 2 random slopes, I can use either one as a moving forward here to compare global fit. So here is the fit of my random quadratic against the real data and against my piecewise model. Note the piecewise model has a linear slope in both parts, so it says that people are going to keep getting better and better. Likewise, here's the fit of the variances for the piecewise models that we looked at relative to the random quadratic. So how do I know if this is good enough? Am I done? Do I write it up and call it good? It looks pretty good. I got to compare it to an unstructured model, but, so we've got unstructured on both sides, right? Like the best possible model I could have would have what on the mean side? Saturated and unstructured on the variance side. Can I do a model comparison with my best fitting piecewise model against that one? Lucas says no. Why can't I? Model for the means is different and I'm in Rimmel. So yes, in theory, if I were in ML, I could do that. But instead, we're going to do the trick that I taught you last time again. I'm going to blow Charlie's mind again. He's like, it's freaking me out, man. Just for you and for anyone else whose mind was blown a little bit, I put up a new version of the Chapter 6 SAS files where I have extra code in there showing you that no, it doesn't matter which 3 deviations for session you put in, you get the exact same result. It's just a convenience to let SAS do it via session because then you don't have to compute new variables or figure out how many you need necessarily. Are significant as a set. SAS decided which 3 it wanted to put in. There's probably some reason for it, but it doesn't really matter because you could put in any 3 and it will fit to the same. The question is, as a set, do these 3 things help? If my model fits, I shouldn't need 3 more things. Survey says, here's my multivariate walled test for my 3 new things. Dun, da, da, da. My p-values are non-significant, whether you call it an F or a chi-square. Is that good or bad news? In this context, I know you're not like, it's non-significant. Should I be cheering? Yes, cheer. Hooray! It means that my model is not worse than the best model. I win. Until reviewer 3 says, this is really atheoretical because who said that the break at session 2 should happen? Why isn't it session 3? And on that one, I'm like, yeah, you're right. Because it looked like it should be at 2. That's why. I don't have a better reason than that. And yes, future studies should attempt to replicate this important finding that session 2 is very different. There. Put that sentence into the discussion for reviewer 2. Because they're right. They're right on that one. So even though I totally made this up, and it doesn't necessarily have any great theoretical meaning, it fits. And there's something to be said for that. So the mean side fits. How about the variance side? So if unstructured is best, how many parameters does it take for my 6 occasions? There's a formula, number of occasions times number of occasions plus 1 divided by 2. 6 times 7 divided by 2. 21. All right, 21 possible variances and covariances. How many parameters did I spend trying to replicate them with my piecewise model? Now I'm talking about the variance model specifically. So let's count them up. How many terms on my random line here? 3 variances. How many covariances between them? 3. It's a 3 by 3 G matrix, so 3 things on the diagonal, 3 things on the off diagonal. So that's 6. Am I forgetting anything? What's this repeated thing do again? What's that one refer to? Level 1. Does level 1 have any variances and covariances in it? It has an E variance. And in this model, it's the same across time with no covariance, so that counts as 1 more. So in total, I have spent 7. I have estimated 7 quantities to try and reproduce the 21 variances and covariances. Keeping the fixed part of the model the same, I can compare the variance models. So here's my fixed model, repeated here, swapping out my random effects for an unstructured variance. 21 versus 7. Difference of 15 for 4 degrees of freedom. Survey says I win. I win. And this is real data even. So yeah, I win. P greater than 0.05, semicolon, I win. Right. Wouldn't that be fun if you had to write that as part of your statement, right? P greater than 0.05, comma, I lose. P greater than 0.05, I win. That would certainly help your readers follow, I think. So, just a thought. Try and put that out there. So yeah. Now, why did I have the chance to be able to win? What's the magic feature of this data set that gives me this possible answer key? Balance. I have session 1 to 6 for everybody. What if this were unbalanced? Then what could I do? You could still round things to come up with a saturated means unstructured variance model. In theory, that might be a comparison, but it's a little weird because you're not treating time that way and trying to generate predictions. The reality is that there isn't absolute fit unless everybody shares a common covariance matrix and common set of means to come back to. SAS doesn't assume that you're going to have that type of data, and that's why it doesn't give you these absolute fit tests that show up by default in SEM programs that are built for balanced data. So if you think about a factor analysis or a structural equation model, everybody has the same set of items. That's like saying everybody has the same set of times here. What if you were to use a multi-level model for people in groups, like kids in classes? You would need to have the same number of kids in every class for this type of absolute fit assessment to be possible. So there's only certain corners of multi-level model land and certain types of data for which these absolute fit tests are possible. Balance is the key. If you don't have that, then you got to think outside the box. Making pictures is one way to do it. Paying attention to theory is another. The fact that these piecewise models in this case fit well is admittedly an atheoretical thing, because I don't have a reason to put the knot at 2, other than it looks like that's where it should go. That's all I have to say. All right. I giggle next because we get to see NL mixed. The cool stuff. Let's see. I think I hit most of this. All right. So, Amy, I'm going to pick on you for a second. You answered a question like maybe Monday or a week ago. What's going to happen to my quadratic according to these predictions? Yeah, well, you wanted it to stay put, right? Because, like, how often is it that you get better and then all of a sudden you come back down? You wanted it to keep going up there. And I said, stay tuned. Exponential models, friends. I will show you some pictures, and that will be a good thing to end on. Pictures are fun. So here's an example. This is real data. This is the same type of response time data we've been looking at, but across trials within a session, because each of those means for each person's session is actually based on 30 trials. So I'm aggregating the data to be able to create an example for you. If I wanted to model the trajectory of improvement during a session across trials, the red line is what the quadratic would say. There's a latent two-piece model that I fit for this particular data set given by the green line, where I told it to look for where the break should be, and here's an early slope and here's a late slope. But neither one of those are very appealing to me and based on the theoretical process of learning. The blue line is the fit given by a model that we're going to see next, which is called negative exponential. It is a truly nonlinear model. So models can be nonlinear in their variables versus their parameters. Do you guys know the difference? No? Okay, I'll tell you. All we've been dealing with right now are linear models because it is always slope times variable plus slope times variable plus slope times variable. It doesn't matter if variable is time squared. The way they work together is in a linear fashion. So those models are nonlinear in their variables, but linear in their parameters. Nonlinear models are things that look like this. E to the rate times time, where terms get multiplied together rather than added. Or we have things like logs or exponents. Those are nonlinear in their parameters. But this particular model that I want to show you is very useful for learning type data. It has 3 parameters. One of them is the thing that Amy wanted, which is an asymptote. So we have 3 lines here that have the same shape, but they differ in where they end up at. So in a learning context, if we think about people getting better and better and better, faster and faster at doing something, there's going to be a point at which you could practice every day for the rest of your life and you're not getting better. Where that is can differ between people. So that's a difference in asymptote. The other parameters control the shape. One is either phrased as an intercept or as an amount, and in this case the 3 lines end at the same place. They get to that same place at the same rate, but they differ in how much change it took to get there. So you can either think of this as the total amount of change or as an intercept. They're 6 of one, half dozen of the other. Rate is the nonlinear parameter that goes up in the exponent in these models, and it controls how fast you get to your exponent. So here people start at the same place, they end up at the same place, but how they get there differs. And this is what you think of when you think of a rate of learning. So these types of models that have nonlinear parameters are nice because they can be more theoretically meaningful. They are not nice in the sense that SAS mixed won't do them and a lot of other programs won't do them, and then you have to look at code that looks like this. So this is what I'm going to show you next week. This is an introduction to Proc NL mixed, which stands for nonlinear mixed, which is a way that you can estimate random effects models of your very own design. you can make up new models and tell SAS to estimate them. And so since SAS doesn't have proc mixed exponential style, we can do it in here. And let's see, Maddie has a look on her face like, I'm not doing that. I don't like that. I no like that. That's what Huey would say to that. And I say, you know what? I no like that either. So what I'm also going to teach you next week is how to trick SAS into making something that looks like an exponential. Because don't those curves kind of look asymptoty? You know how I made those? I put log time into SAS mixed. Boom. And I wish I'd put this in chapter 6, but I didn't. Because all you got to do is log transform time and then do the same shit that we already did to it, and you can get something that looks a lot like this. So I'm going to show you that next week too, okay? Cool. All right, homework is due on Friday. Let me know if you run into problems. Office hours start now.